Okay, we're back. This was the other big textbook homework for this week. Was section 5.8, which in the way our book is organized is the first time that they teach you how to do antidifferentiation and integration problems involving the inverse trig functions. But we've been doing this for a couple weeks now, so this will not be new for us. This will be mostly kind of review. So here we go, 7 problems, but I think they actually sort of take a while, or some of them do at least. Okay, so let's go. Number 13 is just an antidifferentiation problem, so this would be not out of place in maybe the packet from a couple weeks ago. So 4e to the 2x over 4 plus e to the 4x. Yeah. Okay, and now you are just expected at this point to be very algebraically sophisticated and know lots of things about functions, exponent rules, and things like that. And in particular, if you multiply e to the 2x times e to the 2x, then that is, by exponent rules, e to the 2x plus e to the 2x, otherwise known as e to the 4x. And therefore, you should see e to the 4x, and a experienced person recognizes this as just e to the 2x squared. Okay, so why is that so important that you make that observation? Well, if you make that observation, then you see right sort of to the heart of what's going on here. I'll even just rewrite this. So this becomes e to the 2x over 4 plus e to the 2x quantity squared. And if you make that observation, now I think it's pretty clear how to proceed. This is going to be an arctan situation. If I let u be e to the 2x, then when I differentiate this, the derivative of e to the 2x is going to be e to the 2x back inside 2. So this will be 2e to the 2x. And so, yeah, that's just what du is. It's 2e to the 2x dx. So I stick in a 2, I undo the damage with a 1/2, and this whole thing kind of cleans up to be 1/2 du over 4 plus u squared. And okay, if you didn't see it already, now you should see it, that we're back into one of these kind of arctan problems. Okay, so we just keep doing harder and harder things, and we just keep learning and learning, and now sort of the old hard things become easy things now. I would call this kind of easy, though it was hard the first time. You should just recognize 1 over x squared plus 1 as being the derivative of arctan. Therefore, this becomes 1/2. Down here I factor out a 4, so when you factor out the 4 you get 1 plus u squared over 4. And then let's just take the 4 out entirely, so that becomes 1/8 du over 1 plus u over 2. I changed my mind. Let's take let's take some of the 4 out, but let's put some of it back in. And that's because I'm getting ready to do yet another substitution, the substitution of letting w be u over 2, and then dw is 1/2 du, and now I just have that right up there. So therefore, this becomes 1/4 dw over 1 plus w squared. And therefore, it is 1/4 arctan w plus c, which is really 1/4 arctan e to the 2x over 2. Over 2. And that's always positive. Boom. Okay. So, yeah, that was already, I don't want to call it tricky, I guess, but you know, you had to already be kind of experienced of doing a lot of problems like this to sort of know to do all the things that I did. Okay, next, 19. Here we go. Antiderivative x plus 5 over root 9 minus x minus 3 squared. Okay, dx. Alright, I think this is the one that's kind of hard. Yeah, I don't know, let's see. Okay, well, right now, this is just screaming out for me to do a u sub. So let's just kind of do that and simplify our lives. So if I do a u sub over here by letting u be x minus 3, then, then du is just dx. So really, okay. So that's just going to be a little bit nicer in there, I suppose. And then if u is x plus 3, then that means that x is just u plus 3. Okay, so what have I accomplished? Not much. I just get now in this numerator, I have, instead of x plus 5, I have u plus 3 plus 5. In other words, u plus 8. And then down here I have root 9 minus u squared. Alright, personally, I find that to be clearer, more clear than the previous problem, and sort of worth it to take that extra 1 minute to do that. Okay, well, anyway, how do I do this? Well, some experience with problems like this should convince you that, okay, if there were no 8 there, temporarily cover up that 8, pretend it's not there. Well, now it looks like some chain rule happened here. And the derivative of 9 minus u squared is, give or take a constant, is just u. So then I'll be able to do a u sub. But the 8 is there. So the derivative of 9 minus u squared is not u plus 8, give or take a constant. So that kind of sucks. Also, what's the derivative of, what if the u weren't there? Well, if the u weren't there, then this is roughly speaking in the arcsine form. So, the trick to doing this problem is to really think of this as now just two totally separate problems. There is the antiderivative of, there's the u du over root 9 minus u squared problem to solve. And there's the 8 du over root 9 minus u squared problem to solve. And if I can sort of divide and conquer, do each of these, then I'll be done. And I just can do each of these because, just kind of put a dotted line here, because I'm going to now solve these two like totally separately. Here, I will let w be 9 minus u squared, then dw is negative 2u du. I am going to stick a negative 2 in there, boom, boom, and undo the damage with a negative 1/2. And so this left antiderivative becomes negative 1/2 times dw over root w, which can be maybe rewritten more helpfully as w to the negative 1/2 dw. And now I antidifferentiate. And what is the antiderivative of w to the negative 1/2? You go up a power to 1/2 and you divide by 1/2, so that you just get 2 root w. And so this whole problem becomes negative root w. And so really, what you get from this left-hand side is negative the square root of w is 9 minus u squared, but then also u is really x minus 3. Okay, so that's what happened on the left. On the right, I have to be not scared. Well, I find this kind of distracting, so erase that now. Maybe I'll do some kind of green or something. But now I have to say, okay, well, the first time you do this, it's really hard, but then it's just not hard, because now I have 8, and what do I want to do is I want to factor out this 9, so I get root, and then I factor out a 9, and that becomes 1 minus u squared over 9. Why? Because I can now take that 9 out of jail, and when I take it out of jail, it becomes a 1/3. And so on the top, I get 1/3 du, and on the bottom, I get the square root of 1 minus u over 3 quantity squared. And why is that good? That is good because I can let w be u over 3. This is a totally different w, like as if these are two totally separate problems. Then dw is, of course, 1/3 du. So everything's working out perfectly. And I end up with 8 antiderivative dw over root 1 minus w squared. So I had to see that kind of coming 5 steps away. What is that as the derivative of arcsine? And so we get 8 arcsine w. And that's why, therefore, the answer to this problem is that plus 8 arcsine. What's w again? It's 9 minus u squared. No, sorry. This w is u over 3. So it's x minus 3 over 3. Perhaps it is kind of dangerous to use the same variable again. Anyway, ta-da! That was a complicated problem. That was quite hard, and it was only possible to do if you really know what you're doing. This says that I made a mistake. What is this problem? Negative minus arcsine? No, plus arcsine. Very obscure answer that they've just given. I think it's just a typo in the book. I'm pretty sure this is just right. Okay, good. More. This is about as hard of a problem as I would ever expect you in a normal year to be able to do kind of on your own with a piece of paper, like on a test or something. Okay. Alright, moving on. Moving on. Okay, 33. 33. What's 33? Oh, okay. Here we go. 2x over x squared plus 6x plus 13. So one of these guys again. I can't, it's a rational function, I can't do any polynomial long division because the degree of the numerator is less than the degree of the denominator. What can I do? Well, I don't really know even what I have until I can complete the square to understand that denominator a little bit better. So when I do that, I get that this is, of course, x squared plus 6x plus 9 plus 4. And so this is really 2x over x plus 3 squared plus 4. Okay, and once again, different people feel differently about this, but to me, I just want that x plus 3 just out of my life as soon as possible. So I'm going to let u be x plus 3, du is just dx. If u is x plus 3, then x is u minus 3. And therefore, this becomes up here sort of 2, that x becomes u minus 3, and the bottom is u squared plus 4. Alright, have I accomplished anything? Not really. But now, hopefully you see that this is really like 2, well, it's 2u over u squared plus 4 on the one hand, and minus 6 du over u squared plus 4 on the other hand. And now each of these is easily doable. Yeah, because here it's just the same. This is getting a little bit repetitive. Here, if I let w be u squared plus 4, then again, dw is 2u du, which is actually exactly what I have. And so this becomes a dw over w situation, and so this is natural log of u squared plus 4. So this is the natural log of x plus 3 squared plus 4. And then this antiderivative can be done with arctan. And so you factor out that 4, so this becomes minus 3 halves, and then you get the du, and then, so you factor out 4, so it's actually u squared over 4, so it's really like u over 2 squared. I'm doing the thing now I tell people never to do, which is try to do all the algebra in your head, but I just did this exact problem 5 minutes ago, right? You factor 4 out, it becomes 6 over 4. When you factor out the 4, it becomes u squared over 4 plus 1, so this seems okay. And then, of course, because once again, I'm letting w be u over 2, and dw is 1/2 du, then I want a 1/2 in there. Let's just like move that 3 halves, move that 2 from outside, like back in, then everything's like good as is. And so we get minus 3 dw over w squared plus 1. So that's how I end up with minus 3 arctan w, but it's that w, u over 2. So it's x plus 3 over 2. Cha, plus e. Okay, good. I can just check that. Minus 3 arctan x plus 3 ln, sure. Good. X plus 3, yeah. Woo! Okay, so that was only 3 problems, but it took us probably like 20 minutes. 15, 17 minutes, but I was going really fast. I'm very good at algebra. I'm very comfortable with this because I'm just very good at this. But maybe you're very good too, because I've assigned a million problems on this. So, all right. So this was actually just all review in the sense that this was all antidifferentiation. So this was everything we just did in this first 17 minutes was supposed to be some things you already knew how to do. Now we get to the new stuff, which is also just like not even really like new per se, but we're going to do some integration problems. Okay, let's go. 23 is the integral from 0 to root 3 over 2 of 1 over 1 plus 4x squared dx. Okay, well, this to me is screaming arctan, of course, because if I let u, because this 4x squared is really just like, yeah, it's just like 2x quantity squared. And so, yeah, okay, this is almost silly to do, but u is 2x, then du is 2 dx, so I need a 2 in there, so I stick in the 2, I undo the damage, and now I have, here's my new problem, 1/2, and now 2 dx, so that's just du over 1 plus u squared. And now I need to change my limits of integration. So when x is 0, u is 0, and when x is root 3 over 2, u is just double that, so this is just root 3. The beautiful thing about integration by substitution is that you just have this new integral, and you don't look back. I just now do this integral. And actually, what is this integral? Well, that's just arctan. So this is 1/2 arctan u, and evaluated at root 3 and 0. And so I think we're almost done with this problem. This is going to be 1/2 times. What is arctan of root 3? Is the angle whose tan is root 3, so that's just pi over 3. Woo! And what's arctan of 0? It's 0, and so this whole problem, it just becomes pi over 6. And I bet that's just right. And it is. Okay, good. Many down, 3 to go. Maybe this won't be that bad. Ha 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 ha. 31. Integral from 0 to 2 of dx over x squared minus 2x plus 2. X squared minus 2x plus 2. Oh, I think this is going to be also relatively easy. What should we do? We should complete the square down in this denominator. And if we do that, what we get is x squared minus 2x plus 1 plus 1. In other words, x minus 1 squared plus 1. Okay, and even me, who is kind of, well, I really want to push this integration by substitution because it really is just helpful. So for example, let me just let u be x minus 1, right? If I do that, then du is dx. This all just seems kind of like a waste of time or something. But it isn't, because I really do just get like simpler things to deal with. Because when I do this substitution, I get du over u squared plus 1, but now I get to change the limit. So when x is 0, when x is 0, u is negative 1, and when x is 2, u is 1. And so this whole thing becomes arctan u, but evaluated at 1 and negative 1. And so it's arctan 1, which is pi over 4, minus arctan negative 1, which is negative pi over 4. And then the answer is just pi over 2. So the great thing about integration with substitution is actually when you explicitly do the substitution to change your limits, your problem just keeps getting easier and easier, I think, and more simple to deal with. And that's just the answer. Okay, woo! All right, 2 more to go. 39. I bet this is going to be annoying. I don't know, let's find out. 39. Integral from 2 to 3 of 2x minus 3 over root 4x minus x squared. Okay, I might need like more board space for this, but maybe not. Okay, what does an experienced person like myself do in this situation? Oh man, I need to complete the square down here in the denominator. So let's just like do that first. So down here in the denominator, this becomes, I factor out a negative, so it's negative x squared minus 4x. This is just how one completes the square. Okay, I need that to be a 4, so that becomes, plus 4, and now I just subtracted a 4, so I need to add a 4 in the radical in the denominator. Okay, so this little bit of algebra has revealed this problem to really be the integral from 2 to 3 of 2x minus 3 over root 4 minus x minus 2 squared. And I basically did a bunch of algebra to reach that kind of point of clarity. Okay, this is very helpful. I am now going to once again do the explicit substitution. Let u be x minus 2, and then du is just dx. Well, if u is x minus 2, then x is u plus 2, and well, I guess what's 2x minus 3? 2x would then be 2u plus 4, so 2x minus 3 would be that minus 3, so 2u plus 1. Okay, so I'm now going to transform this entire thing into u's. If you're following all this, then that numerator, 2x minus 3, has now just become 2u plus 1 over root 4 minus u squared. And then I change my limits as I go. And let's see, when x is 2, u is 0, and when x is 3, u is 1. Okay, so after this whole big bunch of algebra and stuff, I now just have like this new problem to solve, and once I solve it, I'm just done. Well, how do I solve this problem? Similar to some things we've done earlier, this is now really, we should recognize this as 2 problems in 1. this is really like the integral from 0 to 1 of 2u over root 4 minus u squared, and the integral from 0 to 1 of du over root 4 minus u squared. And why should I see this as two separate problems? Because this one can be solved with a simple u sub, and this one is going to be some kind of arcsine thing. So let's just do these separately. What do I do here? Here I let w be 4 minus u squared. dw is negative 2u du. There's already a 2u up there, so I stick in a negative and I undo the damage. And then this becomes, oh man, let's see, there's a negative, but then it becomes just like dw over root w. Now I change my limits again. When u is 0, w is 4, and when u is 1, w is 2. So I get that. So really this is, now I flip it again, taking away the negative, so this is the integral from 2 to 4 of w to the negative 1/2 dw. And now, okay, I gotta finish this on this board here. When you antidifferentiate w to the negative 1/2, you get 2 root w. So this becomes 2 root w, but evaluated at 4 and 2. And do you see how it's much simpler now to sort of just, well, okay, I'll just finish this off. What do I get? I get 2 times root 4 is 2, and root 2 is just root 2. So it seems as this half of the problem has left me with 4 minus 2 root 2. What about the other half of the problem? Well, here now I engage in my move where I write this as, or I factor 4 out of here, and so this is du over root 4 times 1 minus u squared over 4. And that 4 comes out, and writing as small as I can, that becomes a 2, so I get integral from 0 to 1 of 1/2 du over root 1 minus u over 2 squared. And then I have to do a substitution of w equals u over 2, and then dw is just 1/2 du, so it all works out perfectly. And so this integral turns into the integral of just dw over root 1 minus w squared. And now I change my limits. This becomes then just now when u is 0, w is 0, but when u is 1, w is 1/2. And so now this is arcsine w. And so I get arcsine w, but evaluated at 1/2 and 0. So this becomes plus, what's arcsine of a half? The angle whose sine is a half is pi over 6, and the arcsine of 0 is 0. So I hope that the final answer to this problem is 4 minus 2 root 2 plus pi over 6. And I'll be very happy if that's right and very sad if it's wrong. And, oh no! 4 minus 2 root 3 over pi over 6. Have I made a mistake? Oh boy, I did! Way back here! Way back here, w is 4 minus u squared, but of course when I changed the limits, I was too sloppy, because when u is 1, u squared is 1, so 4 minus that should be 3. So, apologize for that. This should be, in fact, 3. And then, because when u is 1, w is 3. And then when I flip them, that becomes a 3. And therefore that lower limit of integration is 3. Therefore, this is just root 3, and that's root 3, and that's root 3. And that is the right answer. So that is good. Okay, one more problem to go. Oh, it's like a monster. What time is it? Okay. Good. Last problem. And you know what? Well, maybe I just shouldn't have assigned this 46 at all. It is kind of a challenge. So, you know, if you didn't do it, whatever. But I'm going to do it right now. Last problem, number 46. Here we go. I said previously this is as hard as it gets that I would expect you to do on your own. This is just as hard as it gets. Well, okay, not even, but this is pretty hard. Integral from u to 1 of dx over 2 root 3 minus x root x plus 1. We're going to do this whole problem right now, but they consider this problem so hard that they just give you the substitution. And they tell you, hey man, just let u be root x plus 1. It's not obvious at all that that is a good idea. And I am wondering what would happen if you let the other one be a u. I bet it would also work, but I'm not sure. And I'm gonna follow what they tell us to do, so let's begin. So over here, I'll use both boards. Maybe this is not so bad. Let's let u be root x plus 1, taking their advice. And I don't see how that's going to solve things, but maybe it will. Well, if u is root x plus 1, then, okay, one thing I can do is differentiate. So du dx would then be the derivative of that, which is going to be 1 over 2 root x plus 1. And so I get that, one way of writing this is that du times 2 root x plus 1 is dx. But if my goal is to rewrite this entire thing in terms of u's, then I want to replace that dx with du's only. Well, root x plus 1 just is u. So what I really get here is sort of like 2u du is dx. Okay, I'll put a little box around that because that's helpful. And this is helpful too, because these pieces have direct sort of counterparts here and here. I really just need to deal with this root 3 minus x thing, and that doesn't seem that hard. So I use this relationship between u and x, that u is root x plus 1, square both sides, giving me that u squared is x plus 1. So that really means that x is just u squared minus 1. And if x is just u squared minus 1, what's 3 minus x? Well, 3 minus x is just going to be 3 minus, u squared minus 1. So